Hi everyone, my name is Brian, and today I'll be presenting my paper titled Machine Learning for Human Design. There are many computational tools in the realm of engineering and architecture, such as Grasshopper and other forms of parametric modeling. These tools allow for systematic and rigorous design processes, but often have a steep learning curve, requires previous expertise, or are generally unintuitive or unnatural to human design. Sketching, on the other hand, is commonly used by architects and engineers alike. This almost primal mode of communication constitutes a quick and easy method of generating and transferring design concepts, which in turn facilitates the sharing of ideas and feedback. But what if we would combine the advantageous features of both into a single interface, and how would that process look like? It might be as follows. Let's say we have an idea for a building that follows this kind of interesting curve. It is very expressive and has a very interesting shape. But what we eventually find out is that this is not a very good shape structurally, as there are high bending moments in it, and that it strays pretty far away from the ideal parabolic arch. You require a lot of material to build something like this, and in a typical design process, we might not find it out until that is much too late. But what if instead, as soon as we draw a sketch of the design, we are able to obtain some information about the performance, and better yet, use the numerical information to compare a few design options. In addition, we can also use the generative power of the computer to not only give us the performance of the design we drew, but also some suggestions of new designs that look similar but perform better. Or even take two of our ideas, made individually or by different designers, and synthesize new options there between them. We have developed a workflow that, for certain types of topologies, can go from firstly sketch to performance-driven suggestions, and from multiple sketches to new interpolated design ideas. There are a wealth of literature pertaining to our subject, but for the sake of brevity today, I will just be going over a couple. The Ideation Lab in the Mechanical Engineering Department at MIT, led by Professor Yang, developed Physi, a sketch-based tool for finite element analysis of simple 2D objects. This method allows for an accurate analysis of the structure, but leaves little room for design generation or creativity. The Magenta project by Google has also obtained success. The Sketch RNN allows for the completion of a sketch users sketch by learning through a recurring neural network, whereas the Sketch VAE allows for design generation through a variational autoencoder. However, there is no injection of performance or analysis whatsoever. Put simply, our goal is to reach a middle ground between these examples to combine aspects of performance analysis with creative design generation for sketch designs. To achieve this paper proposes a new workflow for performance-driven designs with sketches. The workflow is split into 4 parts, which will be further elaborated. Being a fairly large and challenging problem, the problem was limited to topologies that exist and are relevant to structural design. 3 morphologies were chosen which are common across many buildings. Specifically, the topologies that correspond to trusses, curved frames, and stacked boxes. The performance that we're concerned with might also differ based on the designer's intentions, be it structural material quantity, embodied carbon, construction costs, or traditional structural criteria. For this research, we'll be focusing on structural material quantity, specifically the amount of material required for the designs that we generate. To generate the data, models were developed in the Grasshopper parametric environment. Performance analysis was done by applying loads on the models and analyzing them using Parametric. 20,000 designs and their corresponding performance scores were then generated for each topologies using the sampling and capture tool found in the DSC toolbox, developed by the Digital Structures Group. Using the data generated, the model first aims to predict the performance of an input designed by the user. To do so, data has to be first compressed into a lower dimensional representation by a variational autoencoder, which is then used together with the performance data generated to train a surrogate model for performance prediction. A latent space is constructed via the VAE, and the design reconstruction is finally combined with the performance scores predicted by the model. This overall infrastructure is used to attain real-time performance prediction, generate new design ideas, and to interpolate between groups of designs. And the results produced are promising. On the synthetic test data, we are able to get really good estimates on the performance scores of the designs from the surrogate model. As you can see here, most of the predicted and actual values fall within 5% of each other. That means that a user can sketch a design and immediately obtain its performance prediction. This allows users to compare performances across groups of designs as shown here. Now that we have real-time performance predictions enabled by the surrogate model, what if we want the computer to help us in the ideation process? We go back to the latent space developed from the VAE. By imposing performance as an additional dimension on the original latent space, we are not only able to explore the relationship between encoded vectors and performance, but also traverse through this new design space and find new design idea suggestions. Take note that this is a simplified example containing two latent dimensions, whereas the actual number ranges from 18 to 30. By performing a stochastic sampling on the design space, we can take in initial designs inputted by the user and suggest new designs that are relatively better performing according to the metric that we have chosen. Having the latent space developed, we can also perform interpolations between multiple design inputs. For example, we have two initial design inputs in a two-dimensional latent space. We can traverse through the space between the 2 points and find designs that are located between the two inputs via a process called interpolation. Following this process, different design inputs can be proposed by the user, and the model is able to produce intermediate designs between the two that contains features of both. We can also combine interpolation with the previous ideas of performance-based design suggestions by sampling around each of the intermediate designs to find better performing options along the path. Currently, there exist some limitations of our model. Firstly, the smoothness of some of the generated designs are far from ideal. And as is the case with machine learning model, the model only works as well as the data we train it with. The cases shown here deviate greatly from the data that we trained the model with, so we can see some visible confusion in the way the designs were interpreted and reconstructed by the VAE. This points towards future work in potentially developing databases of real sketch data from engineers and architects, or new data re-representations of sketches. All in all, the hope is to be able to incorporate this new way of design into current design processes, to be able to simply sketch a drawing like how we do now, and have instantaneous and useful computer-driven inputs or suggestions that can ultimately inform us to design a better performing final structure. Please take a look at the submitted conference paper for more information about the research. Thank you so much for your time.